Good evening, and welcome to the second of two videos on the differences between the physical and psychological world. Now, in this video, we're going to address the second two questions. All right, in the previous video, we talked about what's called the detection question. Here, we're going to talk first about what's called the difference question.
It's 9 o'clock.
Well, thank you, Jesus. Now, this is concerned with the limits on our ability to detect very small differences between stimuli. And if you watch the video of the guy on the radio playing Darth Vader's theme song from the first half of this PowerPoint, you'll know what the difference question is. Can you tell the difference between a volume of 5 and a volume of 10? And is it easier or more difficult to tell the difference between that and between 25 and 30 on the same scale? All right. So again, the difference question is concerned with the limits on our ability to detect very small differences between the stimuli. All right. Questions that you might want to address with this are things like, what is the smallest difference in brightness between two lights that we can see? What's the smallest difference in loudness between two sounds that we can hear? All right. If you do something like this, and you just kind of, oh, when did she detect it? I was touching her hair, all right, earlier than what I actually did. Then when she actually noticed it, what caused her to notice that difference? All right, when did I cross the threshold? So what's the smallest difference in brightness that we can detect? What's the smallest difference in loudness that we can detect? All right, so that's what this difference question is really all about. Now, I will tell you that all of this deals with the difference question in a different way as well. We define the difference threshold as the minimum difference between two sensory stimuli detected 50% of the time. All right. So the minimum difference between two sensory stimuli that we detect 50% of the time. Sometimes you'll hear this referred to as the just noticeable differences, the JND. As a matter of fact, the guy in the video mentioned this, called it JND as well. Now, this is relative to the constant background intensity. All right. For example, if you're sitting in your room at night in the dark with the shades drawn, the lights out, and everything else, and somebody turns on a flashlight, you're going to see it. Okay, it's going to be very, very obvious to you. However, if you're sitting in your room with the lights on, the windows open during the daytime, and it's very bright in there, and your little brother comes in and turns on a flashlight, you're probably not going to notice that at all. All right, and so the background intensity matters a great deal for this as well. All right, you'll notice it. You'll notice the flashlight much more dramatically in a dark room than you will in a light room. Okay. And so all of this has to or deals with what we call the difference question. Now, interestingly enough, there is a mathematical rule for the difference question, and it's known as Weber's law. Now, I'm not going to make you do any arithmetic here. It's not a math class. Although if you do take psychology in the fall or sometime in the next 4 years, your psychology professor may actually require you to know this kind of stuff. But this is a video on Weber's law, and it illustrates the things that you see here. All right, and this is actually this is the one with the Darth Vader guy. But anyway, whatever. But Weber's law is a mathematical rule that illustrates that shows what the difference question or what the answer to the difference question actually is. Okay, so Once again, take this video, pause it, and go to the PowerPoint and watch the YouTube video that's here, or copy this into your browser and have a look. All right. Now, Weber's law essentially says this: for each type of sensory judgment that we can make, the measured difference threshold is a constant fraction of the standard stimulus value used to measure it. All right. Now, and I'll give you an example of this in the next slide, just to illustrate it. But the constant fraction is different for each of our senses. It's the constant fraction is 0.08 or 8% for light intensity, and it's 0.05 or 5% for sound intensity. All right. So it's a constant fraction, but it's not constant for every sense. It's different for each of the senses. All right. So the measured difference threshold is a constant fraction of the standard stimulus value used to measure it. So how do we illustrate this? All right. Let's say that you are a weightlifter. Okay. And let's say that the Weber's constant fraction for lifting weights is 0.02. All right. So if the standard stimulus is 50 pounds, what's the difference threshold? All right. Well, if you look at this, 0.02 is equivalent to 2%. Well, the answer to this question, if the standard stimulus is 50 pounds, what's the difference threshold? Well, what is 2% of 50 pounds? Okay. Anybody know? What's 0.02 times 50? If you do your math here, magic number box, anyone? If you need one. All right, but if you do this arithmetic, you'll find that the difference threshold is 1 pound. So if I put a 50-pound weight in one of your hands, and I put a 50.2-pound weight in the other hand, all right, you're not going to be able to tell the difference between the two. All right, if I put a 50-pound weight in one hand and a 60-pound weight in the other, then you would definitely be able to tell the difference. All right, but a 50-pound weight in one hand and a 51-pound weight in the other hand, you would only be able to detect the difference 50% of the time, because the difference threshold is that 1 pound difference. Okay, I hope that kind of makes sense to you. I'm not going to make you do arithmetic here. There's no homework in this and that kind of thing, but I want you to understand, if the standard stimulus is 50 pounds and the constant fraction is 2%, well, 2% of 50 pounds is 1 pound. All right, and so if you picked up a 25-pound weight, and in the other hand you picked up a 26-pound weight, you wouldn't be able to tell the difference between the two. Okay, if you picked up a 25-pound weight and a 35-pound weight, you would be able to tell the difference between the two. Okay, so that's an example of how Weber's law works, and it works again for your eyes, your ears, your senses of touch, taste, and so on. All right, those are all they all have their own individual constant Weber's constant fraction for this. Okay. For the third and final question here, we're going to ask what's called the scaling question. And this is concerned with how we perceive the magnitudes of clearly detectable stimuli. So there's no question. You see it, you hear it, you feel it, whatever it is. All right. But now we ask a question of scale. All right. If you double the intensity of light, do you see it as twice as bright? Okay. If you double the loudness of a sound, do you hear it as twice as loud? Okay. These are all interesting questions. If you turn your radio up from 10 to 20, does it sound like it's twice as loud? All right. In reality, the answer to both of these questions is no. All right, it doesn't. There are different aspects of the scale, and most of them, for vision and hearing at least, are what we call exponential. Okay, so the answer is no to both of these questions. It's not a one-to-one kind of thing. Just because you double the stimulus doesn't mean you double the perception. All right. And if you cut the stimulus in half, it doesn't mean that you cut the perception in half either. All right. It's not a one-to-one thing. It's a scale, but it's not a linear scale. It's what we call an exponential scale. Now, this is, or what this brings us to, and how we go through this is another mathematical relationship, and this one is known as Stevens' power law. All right. Um, the perceived magnitude of a stimulus is equal to its actual physical intensity raised to some constant power. So if these if you've got, oops, I didn't change the pen. That's why, dummy. So if you have x to the 1th power, that means that the perceived magnitude is the same as the actual physical magnitude. Okay. However, if you square it, it doesn't double. It's actually, for the love of God, it's actually 10 times greater. All right. So the perceived magnitude is 10 times greater than the actual magnitude. And of course, if you cube it, can you guess? It's 100 times greater. Okay. Now, the constant power is different for every sensory judgment. All right. And it can be greater than or less than 1. So it doesn't have to be a whole number exponent. It could be 0.5. It could be 0.7. It could be 2.1 or 3.8. Okay. So the power is different for every sensory judgment: sight, sound, taste, smell, and so on. The and the exponent is not necessarily a whole number, and it's not necessarily 1 or greater. It can be less than 1 as well. All right. If you, for those of you who are good in math and learned this in high school, all right, if you have a fraction, like for example, x to the 1/2 power is the same thing as taking the square root of x. But I digress. Again, this is not a math class, so we're not going to get into too much detail with this. Now, this, excuse me, is something that is explained in this day and age as an evolutionary adaptation. If you reduce your perception of changes in light and sound intensity, this may protect your eyes and ears. All right. If you're out in the dark and all of a sudden a bolt of lightning strikes nearby, not too close, hopefully, but strikes nearby, the entire world seems to light up, at least for just an instant. And that lightning bolt is awfully bright. If you were to perceive it as, 1,000,000 times brighter than the night that you were out on, then that would certainly do damage to your sensory nerves, to the retinas of your eyes and the cochlea in your ears, and so on. All right. And so lessening our perceptions of changes in these stimuli is actually a protective mechanism. And this may be an evolutionary adaptation. Now, on the other hand, increasing our perception of dangerous stimuli would alert us to possible dangers before they affect us negatively. All right, you're sleeping out in the woods and you hear a mountain lion roar. All right, you're going to perceive that much more rapidly and much more accurately than you might perceive the crickets chirping in the bushes nearby. All right. Why? Because the mountain lion is certainly a lot more dangerous to you than the crickets are. Okay. Now, the one thing that is also there is that we adapt to stuff. All right. Our sensitivity to unchanging and repetitious stimuli disappears over time. All right. Remember the light bulb example? You're sitting in the library or your classroom at school, and the white noise of the light bulbs above your head. You don't really hear it. Of course, now if you're sitting in a classroom watching this, now you hear it because it's right above you, and I'm just pointing it out. But when you walk into the room, you don't notice that at all. Um, Unchanging and repetitious stimuli disappear over time. Your senses are adapted not to actually perceive every single sense and perceive every single stimulus that's out there. They're really designed to detect changes in those stimuli, all right, not the constant stuff. If you're outdoors and you hear there's a stream that runs by your campsite or whatever it is, and you constantly hear the water running down the stream, um, after a while, you don't hear it anymore. And the reason for it is that you're not, it's background noise. It's never changing. And so it's not something that your brain um, pays much attention to. All right. Um, I have a CSX railroad line right behind my house, and my kids and I don't even hear the trains coming through. But whenever I have guests stay at the house, they can't sleep at night. Every 10 minutes, they're being awakened by a freight train, and I don't even hear it, right? Because I'm so used to it. All right, and so it's not a changing thing for me because it's so regular, and I've experienced it so many times over the 20 something years that I've actually lived in this house. All right. One thing that we do not adapt to is painful stimuli, very bright light, very hard touches. So, somebody punches you, um, uh, very loud noises. All right, you don't adapt to those. All right, because they are dangerous, and you need to find a way to get away from them rather than simply adapt to them. Okay. So, my friends, that is the end of the second video on the first part of chapter 3. All right, the physical and psychological worlds and how they interact. And I hope you learned something.